Hello, good afternoon. It's me again. On this today's lessons, we will go through the chapters called frequency response technique. Right? Okay. So the goal of today is to be able to draw the Bode diagram. Okay, which you will learn later on. What is the Bode diagram? And then evaluate the frequency response for a given system. Right? So just a recap on what we have gone through few weeks ago. We have used the root locus technique in order for us to design for our compensator, right? Where in that topic, okay, we also mentioned that the reasons why we use the root locus is that it would be enable us to actually visualize, okay, and solve for the closed loop transfer function, which are usually more difficult to handle. Okay, so today what we will go through is will learn another technique. We call it as frequency response technique. And what are the difference between the root locus and the frequency response technique is that in the root locus technique, it has so-called limitations such that it is difficult to analyze the performance of a system which is in the order higher than 2. Remember, we always look into the so-called justifications of the second order system, right? And also using the root locus technique, we may not able to directly derive the transfer functions or maybe other important parameters from experiments. So mainly the root locus will be more suitable when we have everything, the theoretical, the transfer functions already being derived or properly derived or obtained beforehand, so that we can apply for our analysis. So what is the frequency response? Frequency response refer to the words, as we can see, frequency, how frequent it repeat a cycle. Okay, so instead of the typical input that we usually use, like the step, the ramp, okay, we would use another kind of input. We call it like a sinusoidal, okay, the oscillating type of input, okay, to see how the system actually respond, and we generate the kind of the output, okay, such that we will be able to analyze it. Okay, we call this as a frequency response technique. Okay, so generally, as we have stated here, okay, frequency response shows how a system responds to a sinusoidal input. Okay, so you can see that in this system, um, the we may want to give a kind of a sinusoidal or oscillating type of input in the form of force. Okay, we give the force in the oscillating form, and we would want to evaluate, okay, how this output is being respond, okay, or how it respond to the given input. Here is the illustrations of the input, okay, in the form of graphical. Okay, so you can see the form of graphical where this is the input maybe in the form of force, okay, and when it go through our system, okay, this is our system. When it go through our system in the form of transfer functions, then we may able to obtain the output. Okay, again, since the input is in the oscillating form, the output that we would expect is should be also in the oscillating form, right? So how we would want to write this, the familiar form that we usually see is maybe cos omega t and so on, right? So then why we would want to write in this so-called phasors form is that it may be easier for us to understand because it is in the form of cycle. Okay, so it will keep to rotate. So how to express it in the oscillation? So this is the oscillations, and how we relate it if the phasor notations is that we will have a phasor length as the magnitude, and the phasor angle we call it as a phase, right? So we have the phasor angle and the phase. So this radius or the length of this will give us the magnitude, okay, the maximum magnitude, which is the mi, the maximum magnitude. Whereas when this radius oscillating, okay, so we will see that the length of this so-called the measured length, okay, so in this case, since we were dealing with the form of cos, we would want to find the cosine length, right, which is the adjacent to our angle here, right, so which is the ft. So this length will actually, when it's continue to rotate, it will be long and then get short until 0, then become negative length, okay, then continue, okay, it's keep repeating in that kind of form, and that particular angle is given by the psi, right? So we have the psi theta, okay, and we can write now in this cosine functions, we can write it in the polar form, okay, with the magnitude, which is the radius, okay, with the angle of the our starting angle, okay, or the phasor angle, okay. So this phasor angle represent when the time is equals to 0, right? So when the time equals to 0, there is this length that already occurs, okay. So the time will start at 0, it means the length or the position of this length or this angle when time equals to 0 is at this particular positions, okay. So in that way we will able to represent the input response as well as the output response in the phasor diagram, right? Now, as we know that we can transform the frequency response in the form of a phasor diagram, so we will just go through the idea behind it, okay, just in quick, okay, such that to find the frequency response we will have this so-called input, okay, RT, right? It's a general form of oscillating form, right? So we may want to write it in the cosine functions purely or sine functions purely, or in a this is a general form, okay, which consists of cosine and sine terms together, okay. So we just remain this as our initial general form of the input, okay. So this general form of input we can break them, or when we take the Laplace transform we will get this terms, okay, which is equals to as plus b omega divided by s square plus omega square, okay. Taking the consideration that the initial conditions would be 0, then the output, okay, which is the cs, will be very straightforward. Our input multiplied by whatever our transfer functions will give us to the output, right? So this is the general format that we have learned or familiar with, okay, throughout the semester, right? So only the notations now, it may change from the cosine form into the polar form, okay, later on, right? So in order to solve this, what we do is we just take the partial fractions, okay, break them into two parts, okay. Then eventually these two parts, when we check it properly, this k1 and k2 parameters or terms itself are consisting of this m input and the m the gain itself, okay. So you have the magnitude of the input as well as the magnitude of the gain, okay, which define the transfer function as the input itself, right? So this k1 and k2 actually is a complex conjugate, okay, so that we can write as k star 1, right, which is a conjugate to it, okay. And this magnitude, okay, where this mg represent this the magnitude of the gain due to the transfer function itself, the mg is the magnitude of the g j omega, okay, and the phasor angle will be the angle of the uh, g j omega as well, right? So why we try to highlight this one is that as we are trying to find out what is the response, okay, especially when we come to a steady state, right? So when we come to a steady state, when two things continuously oscillate, okay, your input oscillate, okay, and your output oscillate. So bec- when it comes to a steady state situation, these oscillations will now become purely they must be have a similar form now, okay, in the form of oscillations, okay, because the transitions or the transient part, okay, which is started to respond, it's already die off, right? So the remaining, assuming the system is stable, right, therefore the steady state response will now purely have the similar form of the input, okay. Therefore we can see that again in this cosine transfer functions, we can write them into a so-called a phasor format, right? Phasor diagram format, okay, with a phasor angle, okay, and this phasor angle of the output and the magnitude of the output is the multiplication of the input as well as the transfer function or the gain g function g itself, right? So this function g is the frequency response functions, okay, which detect how or to govern how the output should looks like, okay. Now the detail of this frequency response, okay, you can go through it in this form, okay. So how we can get the notations that you have seen previously, okay. Now on how we can visualize the frequency response, okay, the important thing is the blue one, right? So here what happens is that the frequency response of a system when the for a functions gs, okay, when the when it comes to a steady state form, right? So we would want to take the signal in approaching the imaginary, the j omega, okay, which is the oscillations, okay. So now because of the steady state, the response now is purely on the frequency, okay. So that's why we would call that as so-called the frequency response, how it respond to the frequency itself, okay. So it can be plotted as a function of frequency, and by separating them into a magnitude and a phase plot, right? So the magnitude and the phase plot, right? So we will not uh, deal with the polar plot, right? So we will mainly look into the magnitude and the phase plot, and in the magnitude and phase plot also, or the polar plot itself, okay, you still have this m and the angle, right? So we will have that phasor length and the phasor angle, okay, which is corresponding to that particular things, okay. But then because of the polar plot itself, okay, we may want to break them into purely the magnitude as well as the polar the phase plot is phase plot, right? So which we will see or make a term we call as a plot diagram, right? So in order to plot for this magnitude and phase plot, we want to plot in the unit called decibel dB, okay, versus log omega, right? Log omega, okay, where this dB is actually defined as 20 log magnitude m, okay, and the phase angle would be the being plot with two axes, okay, the phase angle versus the log omega. So we want to see how the magnitude as well as the phase angle actually change when the frequency, which is the omega, change, okay, from low frequency to the high frequency, right? So that is the our purpose on this frequency response technique, right? So this is the two logarithmic scale graph, okay, that you may need to use when you try to solve for this plot diagram, right? So later on I will upload the PDF, okay, on this blank logarithmic scale graph, okay, so that you can get familiar with it when you do your practice. Right, so you can see that we may want to plot it for this particular graph itself. You can see that this gain and the frequency means this is to plot for the magnitude. Okay, we will want to know how the frequency, when the frequency change from a low frequency. Okay, so you can see then this is the 10 minus 2, I guess. Okay, 10 minus 2, 10 minus 1, 10 power 0, which is 1. Okay, and so on. So this is 10 power 1, 10 power 2, so 10, 100. Okay, 0 0.1, 0 0.01. Okay, so when the frequency change, okay, from very low to very high, how the gain actually change. Okay, same thing for this so-called phasor plot. Okay, we will have the frequency change from low to high, and we want to see how the phase angle actually change, right, and how we can use or interpret it later on. Okay, so first thing first, in order for us to plot it directly or easily, okay, we have to uh, understand how it works somehow. All right, so as I've mentioned previously, the magnitudes represents the length, okay, of the so-called maybe the, if it is a cosine length, then it would be the adjacent length itself. Okay, but then when we refer to the m omega, it refer to the radius, okay, which is the highest point or the peak values of the oscillations or the sinusoidal curve itself. Right, so given a transfer function similar to this, okay, let's say we take 1 over s plus 2 s plus 4, right, and we can always transform it into this form. Okay, so when we try to plot it out, okay, so we will want to apply the expressions or the analytical expressions such that the s is now approaching the j omega, right, so we will take this into our consideration. So in order to do this, okay, when we try to plot this, right, for different kind of frequency, we will use this g when s equals to j omega for our purpose. So there is questions like should we prepare a printer to print the graph paper when it comes out in the test? Since if you can print it out, then it will be good. Alright, but then if you cannot print it out, that's why I will give the blank paper to you earlier, such that you can use it, okay, in your computer and try to practice to draw straight line on the PDF, okay, or maybe the PowerPoint itself later on. Right, so you just have to do it on the computer. If you don't have printer, okay, you don't need to sketch, so that once you plug it on the computer, you just capture the screen as your answer. Right, so that would be on the assessment part. Right, now come back to these sections. Okay, so when we replace the s as j omega, so what we need to do now is just to replace all the s with the j omega. Right, so j omega, j omega. Okay, so now we will see that when we take the j omega with a square, so in this way, when we take it as a square, then this j, which is an imaginary value, which is a minus square root minus 1, okay, when we square it, you will get a minus 1. Okay, so in this way we will get a minus omega square. Alright, so this is how we obtain a minus omega square over here. Right, then this 8 is remain. Okay, so we group this, and this is the imaginary part. Okay, so once we have these two part, okay, now we can start to plot for the magnitude. So the magnitude is basically the length, right, which is the Pythagoras length of the the J, okay, the imaginary, okay, as well as the real axis, okay, this part, right? So you can actually plot the, or to obtain the magnitude of this M, right? So which will be given as such, okay. Whereas for the fa phasor angle itself, okay, now phasor angle is again depends on the, if you take this angle, okay, phasor angle of this angle can be obtained using a trigonometric relation, which is the opposite directions or opposite side divided by the adjacent side, okay, opposite side which is the imaginary value, okay, 6 omega divided by the real axis side, okay, which is the 8 minus omega square. Alright, so you can take these two values to obtain the psi value, okay, but then just take into the consideration that this is a cycle, okay, so you have learned that all the tangent value at this side would be positive, then this is negative, okay, this is positive and this is negative, okay, so there is a sign change throughout this. All right, so therefore what we can do now is just we would want to see what happened when the lowest value, okay, which is the bottom side, okay, becomes 0, right? Because tangent we will deal with the infinity, okay. So when this will become 0, okay, so this occurs when the omega equals to square root 8, okay. So square root 8, when you take square of it, it's become 8, okay. 8 minus 8 becomes 0, right? So when this occurs, you will get a infinity line, right? So that's why in the tangent functions curve itself, you would see that the infinity lines is over here, okay, and it is going to approach the infinity line when this occurs, and then after that it will start again, okay. When it get more than that, it will start again from negative, okay, going up again, okay. So it will become a cycle, right? So that's why if we put it in a phasor diagram, then we don't have to really specify all this range, okay, from which point to which point, okay. The angle would be calculated in this form and this form, okay. But then this is just an illustrations of how we can obtain the phi, okay, the psi itself, okay, for certain range, okay, for this side, okay, what is the angle, okay, and after that what it would be the angle, okay. So this is how you can relate it with the trigonometric functions itself, okay. Next, now it comes to the Bode plot, right? So as we have mentioned previously in the graph paper, is a logarithmic graph, okay. One side is log, one side is the normal scale, right? So once we intend to plot it, okay, so we would want to plot in the form of log magnitude as well as the phase frequency response curve, okay. We call that as a Bode plots, okay. Usually we just plot it using an approximated sequence of straight line, okay. That's why since it is using a straight line, then you can easily use a straight line in your computer, okay, to to add to the so-called existing graph paper, right, to just to append on the graph paper itself, okay, in order for you to plot it out later on, right? Now the idea behind this plot is that we are given a transfer functions, okay, which have multiple zeros, okay, multiple poles, as well as the system type itself, right? So SM itself, okay, here with a gain k, okay. If we are given this kind of transfer functions, the magnitude frequency response would be the magnitude of all these so-called terms, right? So we can actually get the magnitude of the frequency response given by taking the magnitude of all these things. Okay, that is very straightforward, right? So here you can see that by working with the logarithms of the magnitude, okay, actually there is an advantage such that in log functions, okay, instead of multiply and divide, we usually deal with the add and minus. Okay, when we look at this, okay, we have to multiply one by one, right? But when we take log of the magnitude, then these multiplications, okay, become additions, okay, whereas when divide by the pool, okay, which is the division, so every time you divide you are minusing the log of the magnitude. Okay, therefore we say the zero terms magnitude response would be added and the polar terms magnitude would be subtract. Okay, so this is when we take the magnitudes in the form of log. All right, so how we can do that later on. Okay, so we can illustrate that in this form. Okay, so let's take let's say this is the form. Okay, and when we take, since we want to express the magnitude in terms of dB, okay, so dB itself, or the magnitude itself, is already in log. Okay, therefore that's why we are using a semi-log graph, okay, such that in the y-axis, okay, we put the dB, okay, which is just the value of the 20 log m, right, instead of putting another log scale on that particular axis, right? So when we express in terms of dB, meaning to say this magnitude, we just take 20 log with our whole magnitude, we put it in, right? So if we want to do for this, okay, particularly, so it's become 20 log, since this is multiply, so we have log k and log this and log this and log this. Okay, so when we multiply, it's actually additions of all these things. Okay, when we divide, then it's divide become minus, minus and minus. Okay, so this is how we can total up the magnitude response obtained, okay, for every single pulse as well as the zero terms. Okay, for the phase frequency response, the sum of the response also similar, right? It's the curve of the zero minus the sum of the phase for the pulse terms. Okay, so just add and minus, okay, due to that particular usage of the log itself. Okay, now we can see that the remark that using the Bode plot, these plots are simplified, okay, as they are algebraically summations of individual terms. Okay, and because of that also, straight lines are usually being used, okay, instead of doing a exact calculation to plot the curve, okay, of the line. All right, so this is this chapter or these topics today, we will try to use the approximation way to plot for our Bode plot, right? So these approximations plotting is also important for us, okay, because again, as you know, we have software, okay, like MATLAB and Scilab to actually do all this plotting. So this approximations lines is actually useful for us to double check the answer. Okay, that's it. Okay, we don't have to exactly plot it, right? But it would be good enough for us to estimate the answer first, okay, so that when we plot it using computer, we will know that whether we did key in the correct parameter or not into our computer, right? Not necessarily the computer is whatever generated by the software like Scilab or MATLAB is correct, okay, because it depends on the input of our whatever parameters we input to the system or the computer itself, right? So we will start off with the functions of g s equals to s plus a. Okay, so this is a general transfer functions of for zeros, right? Zeros with a zeros, okay, a value, right? So why we will do this is because, as we say, uh, we want to use straight line to approximate the Bode plot. Okay, so we will start to analyze part by part. Okay, we will see how the magnitude actually being plot on it, okay, for this kind of zero. Then later on we will see how it will be plot for pools and so on, so that later on when we uh, want to draw the full Bode plot for a complex transfer functions, we can actually add them up, right? As we know, as we say, for zeros we add, for the pools we minus. So it's very straightforward. When we draw it, okay, we draw it in the for similar form, okay, then we just add and minus from that particular curve or the graph or the straight line in the Bode plot itself. Okay, so that is the idea behind. We will go through part by part, okay, on how the Bode plot will looks like for every single basic functions, okay, that we will encounter in a transfer function. So we will start with transfer functions with a zero, okay, s plus a. Okay, so in these functions, as again we will just take s approaching j omega. Okay, so we just take this one and we will have this form, right? So this form we can actually take out the a outside, okay, so that we call this as a normalization. Okay, we normalize it, okay, which we will go through it later on, right? But this is how we can also do it. Okay, we say this form as a normalized form, right? But this is how it may looks like, okay, after that. Okay, very straightforward. The s we just substitute with j omega, so j omega, okay, so that's why j omega plus a, right? Now in the frequency response, we will try to analyze from low frequency to a high frequency. Okay, so we start with a low frequency where the frequency or the omega itself near to zero. Okay, it can be 0.0001, okay, 0.01 and so on, right? So approaching zero, so let's take when this approach zero, okay, this term omega actually very small, and when it is small enough we can neglect this term, okay, and we can approximate it as the a. Okay, since this is a, therefore the magnitude of the transfer function itself is basically 20 log a. Okay, since our magnitude is this, right? Okay, which is the a itself, right? So this is how we can get the magnitude for this particular low frequency. Okay, then at the high frequency, where this omega is much greater than a now, okay, it slowly increase, but then after some time it's much more greater than a, maybe 10 times, 100 times, 1000 times greater than a. Then in that case, this particular terms now become very small or so-called negligible. Okay, then the prominent part or the greater part would be the j omega part, because the omega is now very high, right? So when this occurs at the high frequency, therefore we can take the gj omega equals to a omega divided by a, right? Okay, with a particular angle 90 degree because of the j. Okay, j is the imaginary axis, okay, where the angle would be 90 degree, right? So we can rewrite that such that cancel out. This is omega with a phase angle 90 degree, right? So this is the idea when the transfer function is s plus a, then we will have two conditions occurs. Where at low frequency, the magnitude is given as such. Okay, at high frequency, the magnitude is now become this. Okay, 20 log omega. Okay, this log omega. Okay, so this is how it would looks like. Okay, so the high frequency approximation again is equals to the low frequency approximation when they are at a. Okay, when omega equals to a. Okay, since you can see that one is omega near to 0, another one is omega very high, okay, greater than 0. Okay, so when we approximate for the so-called a point where two of this line actually meet, okay, we just approximate such that the frequency, the high frequency and the low frequency when omega equals to a, they are so-called match. Okay, they will meet each other, right? They are equals to each other, okay, at a, right? So when we plot the dB itself, okay, then we will just have 20 log m. Okay, 20 log m, our m would be the value itself. Okay, so in this case, when we put it in, okay, eventually we get y equals to 20x, okay, which have a slope of 20 unit, okay, because of this 20, right? Therefore, because of this 20 unit, okay, now we would able to so-called start to plot it out, okay, in this so-called magnitude plot. Remember, in the Bode plot itself, we have two part. One we will plot for the magnitude first, and then we will plot another one for the phase angle, right? So we start with the magnitude plot first, right? So in the magnitude plot now, okay, we will use what we call a straight line approximations. Okay, again, just keep reminding you, okay, what we did now is just an approximation, and this straight line approximation we call it as asymptote. Okay, we will call that line as asymptotes line, right, or asymptotes. Okay, so here as we start on, okay, we will start with this. Okay, for every doubling of frequency will now cause the angle to increase 6 dB, right? And the line will rise with a slope of 6 dB per octave. Okay, so octave is just a doubling of it, right? So from 1 become 2, 2 become so on, right? So this become doubling, right? So that is referring to the octave, okay, doubling of the frequency. Okay, and then we have these terms called a, right? A itself, remember, we are plotting for s plus a, and that a value we call that as a break frequency. Okay, a break frequency. The break frequency is actually between the frequency between the so-called we define as a low and the high frequency asymptote, okay, where they meets together. Okay, so for our purpose again, for approximation purpose again, we just draw a straight line over it, okay, such that it's 10 times so-called away, okay, 10 times away from the initial frequency, okay, rather than the octave. Okay, so first we start off with the low frequency. Okay, so in the low frequency, as we say, we will just plot equals to log a, right? 20 log a. So we will plot for that, okay, until the point a, okay, the break frequency where we change gear to the so-called high frequency, right? So we will draw another one. Okay, so how we going to plot this line, this high frequency line, is that we will follow this slope, okay, idea, right? 6 dB per octave. Okay, so you can see that actually is 6 dB per octave. Okay, so this one comes to the next one is 1 octave. Okay, and because of 1 octave itself, it should increase 6, okay, 6 dB per octave, right? So 6 dB per octave, or easier way, okay, we call this from 1, okay, 10 power 0, okay, is 1, okay, 10 power 1 is 10, right? So we call this as 1 decade, okay, a decade. So you can see that if we put a value of a here, then this is should be a 10a, 100a, okay, and the other side, right? So if we want to plot a more accurate line, okay, since the longer is better, right? So we will also use a easier way of plotting it. We call it as 20 dB per decade, right? So what we do is, here is 20, okay, so 20 degree per octave. So you look for a 20, okay, you plus 20 here, okay, you just draw a 20. So you draw a straight line, okay, so from this point to that one, okay, in 1 decade the magnitude increased 20, right? That is the how we can approximate a straight line on it, okay, and once we plot that, we just draw a straight line on it, right? So we can see that we have plot two asymptotes, one for the low frequency and another one for the high frequency, right? And where it meets is where the omega equals to 0, the meeting point between the low frequency and the high frequency. We approximate that particular point is where it changed gear from low frequency to a high frequency, right? But in real case, okay, so this is for the 20 so-called 20 dB, right? So we can draw a straight line, okay, so that this is 1 decade, right? But in real life, okay, the real approximation is like this, okay, so this is the actual line, right, which it doesn't actually go through this particular point, right? But since we are using it as an approximation, it's good enough, right? when we when we want to use computer to when we want to plot an actual line, then we can use a computer to plot it, right? Then we just compare with our approximation whether all these asymptotes lines are actually matched to the plot in our simulated result. Okay, if it is, then our simulated results is proper, right? So this is how we can validate our simulated result as well, right? Then on the phase plot, right? So on the phase plot now, okay, previous one is the magnitude plot. Now come to the phase plot, okay, we again break them into low frequency and high frequency, and also we would also want to add so-called at the break frequency, the A value itself, okay. So at the break value itself, since our functions is in this form, okay, this form, when the omega is equals to A, right? When the omega is equals to A at break frequency, we just replace the omega equals to A. So when this is A divided by A, we get 1. So you obviously, if imaginary value coordinate is 1, then the real axis is 1, the angle is 45, right? So meaning to say, at the break frequency, the phase angle is 45 degree, okay. Whereas for a low frequency, for the low frequency, when it is only purely the real axis value, okay, which is the A value, then the phase angle would be equals to 0, okay. When it is at a higher frequency, then our so-called values, okay, are mainly on the imaginary side, which is the J value, right? Okay, or in the phasor angle itself, which is 90 degree, okay. Therefore, in that case, at the high frequency, the phase angle would be 90, right? So in this case, it's very obvious. Again, we will just draw a approximated line, okay, for a low frequency at 0, okay, low frequency at 0, high frequency at 90, okay, low frequency at 0, high frequency at 90, right? So now the only thing is that since at A itself is 45, A, right? So this A value is 45, so we plot a point, right? Okay, so one point is over here. So in order for us to actually, if you plot a line, a point over here, okay, and if we plot this line straight, okay, then we have so-called discontinued, right? So what happened is that in order for us to approximate better, okay, therefore we would expect a kind of a transitions in between a low frequency and the high frequency in the form of phase angle, right? So therefore in this case, okay, we will draw a straight line, okay, 1 decade below, okay, we start 1 decade below the break frequency, 1 decade below, which is equals to 0.1 A, right? So we start at this particular point, okay, and then 1 decade after, right? 1 decade after, which is 10 multiplied by A, okay, 1 decade after, right? So we plot from this particular point, okay, that has this so-called slope 45-degree decades, okay, and then it will end at the 10 decades after the break point, right? So we will start from this point and connect to that particular point, right? So this is what we can do as the asymptotic or the asymptotes line approximations, and the real curve is the blue line, right? So you can see that now it's very close to our so-called actual line, okay, instead of uh, approximation in this way, okay, which is far away from our actual line, right? So remember, for a phase plot, we have to take we have to have to start plotting it 10 decade before as well as 10 decade after, right? Okay, so we will plot before and after, right? So this is how we can plot. For now the function is 0, okay. So once we have that particular idea now, okay, what we would want to do is we would also want to normalize them, okay. We will normalize the magnitude and scale the frequency, okay. Why we would want to do this is because remember this form, we call it as a normalized form, okay. So when we actually normalize it, okay, it is easier for us to actually compare, okay, between different order frequency response plot, okay. Easier for us to compare when we normalize them, okay. If they are not the same, then the plot is different and we cannot compare directly, okay. Especially for the low frequency, okay, where the starting point and everything is not at 0, okay, not at the same line, okay, or value, okay. And also when we normalize it, okay, it's become easier for us to add them up or minus subtract them out easily, okay. This is the main purpose of we plot it, okay. And then remember, in log we just add and minus, right? So if we have all these things, all of them being normalized, then we can easily add them or subtract all these component of different terms in our transfer functions later on, okay. So what we do is we try to normalize in this form, okay. And once we normalize it, okay, then our terms is becomes 1, okay. And you know, log 1 you get 0 dB, alright. So therefore it will start from 0 instead of the so-called maybe 20 log particular numbers, right? So now from the previous curve, okay, which may start over here, when we normalize it, okay, then our starting point will now start from 0, right? So this is a asymptotic, normalized, and also so-called scaled magnitude response, okay. Next we would also see for a Bode plot for a functions which consists a pool. Okay, a pool is 1 over s plus a, right? So using the same concept, we just go through it in very fast now. Okay, after we have understand the idea on how we construct the Bode plot, okay, for the zero. Okay, for the pools is now very straightforward. Okay, same idea, we plot for the low frequency and the high frequency. Okay, and because of this 1 over s plus a, okay, therefore we will get our value as negative. Okay, whereas for the low frequency, the value remain the same. Okay, equals to so-called log a. Okay, and when we normalize it, it becomes 0. Okay, therefore when we plot the magnitude, we will start with 0. Okay, until our so-called normalized a value, right? The a value now become 1. Okay, since we already normalized them. Okay, and then at this particular point now, it will start to go downwards. Okay, instead of going upwards. Okay, in the previous zero transfer functions. Okay, now we have a slope which is negative. Okay, downwards 20 dB per decades. Okay, we just draw a 20 degree. Okay, 0 20. Okay, 20, 1 decade 20. Okay, just straight line continuously going down, right? So this is how we can draw the magnitude for a pool. All right, whereas for the phase angle, the idea is also similar, right? Just in the reverse directions. Previously is 45 degree per decades. Now in the pole, okay, which is at the denominator, the lower side, then the slope is just going down, right? So we have 1 decade before, we will start to plot it with that particular slope, minus 45, through the break frequency, and to 10 times a decade after the break frequency, and then come back to the 90. Okay, since it is at the negative direction, so therefore the angle would be minus 90. Okay, instead of 90 degree, right? Next would be when we want to plot for a zero. Okay, a pure zero, only s, no a terms there. So once they are only s value, okay, therefore our transfer functions would be purely in this form. Okay, and meaning to say it only has the high frequency asymptote. Okay, remember this represent the high frequency part. Okay, because it's controlled by the omega change, and it will affect the whole things, right? So it only have the high frequency asymptotes. Okay, therefore in that case, we just plot a straight line throughout the whole range of the frequency. All right, and because of that also, it's only have a 90 degree constant of phase plot, right? 90 degree phase plot for the whole range of frequency. Once we understand this as well, then this 1 over s transfer functions will have the just a reverse or the inverse of the g s equals to s functions. Okay, which is now with a slope of minus 20 throughout the whole range of frequency, as well as minus 90 for the phase angle constant value for the throughout the range of frequencies. Okay, so for time being, only four familiar form of transfer functions where you know how the magnitude plot as well as the phasor plot will look like. Okay, based on that knowledge, okay, we will start to see how we can apply it, okay, to solve or to draw for these transfer functions. Okay, so this transfer functions given has a combinations of the so-called zeros, okay, and then the 1 over s, and then 1 over s plus a, okay, s plus a, right? So you can see the so-called familiar form, okay, in this particular transfer functions. So what you can do now is that we will use this transfer functions in the open loop form. Okay, this is open loop form. Okay, even though it may be in a closed loop, remember we are trying to simplify our solutions, okay, based on the idea of if it is open loop, you don't need all these complex uh, methods. Okay, it's very straightforward, but because of the closed loop, okay, we want to simplify the analysis of the closed loop using a open loop functions. Okay, so we use a open loop functions now. Okay, we try to normalize our functions. Okay, how we going to normalize it? Remember, each of this term we normalize. Okay, here is 3, we divide by 3, so we get 3 plus 1, right? And this 3 we bring it over here, right? So same thing for this one, s plus 1, okay, normalize. Okay, this one 2, so we have 2 here. Okay, to bring it out. Okay, so 1 2 3, right? So we will get 3, bring it out. Okay, 1 multiplied by 2, we get 2. Okay, so therefore this blue one is the so-called normalized value that we factorize out, okay, from our whole various terms of the poles and zeros, right? And this 1 2 and 3 now is our break frequencies. Okay, remember every single of these will have their own break frequency. Okay, we just have to mark it out. Okay, and always remember, okay, which break frequency represent to which. Okay, so always refer back to the transfer functions that we have now, right? So once we have this, okay, what we need to do is, since the break frequency is 1 2 and 3, okay, regardless we pick 1 2 or 3, okay, 1 2 or 3 is very similar, right? So in that case we just take 1 decades before, okay, 3 decades after would be good enough. Okay, from this so-called particular break frequency. Okay, so we set a so-called range. Okay, so the easiest one, we just take the lowest one. Okay, 10 decades before. Okay, then and then extend it to maybe 2 decades after, right? So come to 100, then we have a range of 3 decades. Okay, which would be sufficient to show how it would change, okay, throughout a range of frequency. Okay, now what we have seen in this so-called diagram itself, we call this as a component magnitude plot, okay, which consists of various lines, okay, corresponding for every single of these terms, all right, or denominator parameter, yeah, terms, all right. Okay, so now what we need to do next is that we will start at omega equals to 0 0.1. Okay, since we already said we choose 0 0.1 to start, okay, until the end, right? So we may want to start at omega equals to 0 0.1. Okay, then the low frequency value would be as such, okay, where the s would, we will put s equals to 0. Okay, even though this is 0 0.1, okay, we thought that it is a low frequency, low enough such that the s equals to 0, right? So for all these particular terms, okay, for zeros and pools, okay, which is non-zero, right, we will take s equals to 0. So take s equals to 0 equals to 0 equals to 0, so it remains as 1 1 and 1, right? Then for the actual s term, the lower part over here, okay, since if we put this as 0, then our equations will become infinity. Okay, we don't want that to occur, therefore we will replace this as our omega value, okay, which is the 0.1 over here. Okay, so eventually we will get the GS when j omega equals to 0.1. We get 3 over 2k divided by 0.1. Okay, so eventually get 15k. Okay, 15k. So this is how we can so-called scale it, right, and also make normalize them, okay, together, right. So we have this so-called 15k, okay, to represent this particular values. All right, next would be we can see that this k value or this effect of k is to move the curve up or down by so-called a magnitude, okay, 20 log k, right. By this understanding, meaning to say we can actually get the starting value, right. So this starting value would be 20 log k, okay, because of the k value. If the k value increase, then the starting value may change, okay, accordingly, right. And therefore, because of this pattern, these changes, now we can also, it will be useful later on for us to design for our system where we want to select a k value such that the system will be stable for a certain range of frequency, right. So this is where you can control the k value later on, right. For our purpose now, we just choose the k value equals to 1, okay, for our purpose now, easier, okay. So 15, okay, therefore we will start to plot it accordingly. How we can plot it accordingly is that when we take the value k equals to 1 and at the frequency 0.1, the value would be 20 log our k value, right. So when k equals to 1, then our value would be log 15, okay, since we already get this 15k, k equals to 1, so we get 15, right. So in that way, when you calculate, it is equals to 23.52 dB, okay, 23.52 dB, and this is our starting point. Okay, so we will start to draw from this particular point onwards. Alright, so that is the idea of how you can plot the starting line, right. And at the same time, you can start to construct this particular table, okay, to obtain the slope contributions for every single poles and zeros, okay, every single poles and zeros, okay. And since we know that for magnitude, the magnitude only change when it passes through the so-called break frequency, so we just have to identify where is the break frequency, right. So in our curve, we will start at 0.1, so we just put at 0.1, okay. Then for others, like we have s plus 1, okay, s plus 1, so we will use 1, okay, as our break frequency. At pole at -2, we will use 2, okay. At 0, at -3, we use 3, right. So that are the particular frequency or the break frequency that we will have to take care, okay, because they will somehow change, okay, due to our poles, right. So once we have that, right, now we will start to put them line by line, okay. We will start maybe from just arrange like in a order, okay. We start with 0, okay, since we have a pole at 0, then pole as at -1, pole at -2, 3, okay, and so on. If you have 0 at here, you have to put it in as well, okay, just in the orders, okay, so that it's easier for you to plot it out later on. All right, so you can arrange it later on, okay. Now what we do is that for pool at 0, okay, as you still recall, okay, if you don't, just go back, right? For this one, okay, for pulse 0, okay, your magnitude will be always have a gradient of minus 20 dB per decades. Okay, so that would be your contributions, okay, due to this pool. So regardless of whichever frequency, the slope contribution would be minus 20, minus 20, minus 20, minus 20, right? So just write this down, right? Then for pools equals to 1 minus 1, then it will only start to implement the so-called minus 20 slope when it is at the break frequency 1, right? So before that, everything is 0, right? So you just put 0. At 1, you just minus 20, minus 20, minus 20 until the end, right? Same thing for the pool minus 2. So 0, 0 until 2, then it's become minus 20, minus 20, minus 20, right? If you have more, all right? Then for a 0, again, everything's 0, but then when it reaches to the break frequency, it become plus because it is a 0, right? So 0 is plus 20 dB per decades. Okay, so you have this, right? So once you have all the slope contributions listed out, you just total them up together, right? So for this case, it's minus 20, minus 40, minus 60, minus 20. Okay, so based on this so-called total slope contributions per decade, okay, dB per decades, what you can do later on is that you can start to plot your magnitude plot. Okay, we call that as a composite. Okay, total up of all these combinations or of components, right? You will start with 23.52. okay, you just plot a point or mark a point over there. Okay, then once you have that, okay, so at 0.1, you will have a slope of minus 20. Okay, at 0.1 you expect a slope of minus 20. Okay, then at 1, okay, you expect a slope slightly greater at minus 40, and so on, right? So how you can plot it on computer? Okay, you just draw a straight line. Okay, so just draw a straight line. So this 0 to this, okay, 1 decade minus 20, right? So this line represent minus 20 per decade, this line represent minus 40, this line represent minus 60, right? So what you can do is that this line, okay, on your computer, if you are using PowerPoint or maybe PDF or maybe words, okay, you just move that particular line, okay, just shift it up. Okay, after you draw that particular line with respective gradient, now don't change, just push it up. Okay, move the line. Okay, so you draw that particular line starting from this point, right, with minus 20. Okay, until 1. Now you have to change to minus 40. Now you have minus 40, shift it up, right? You just shift. Okay, you have drawn it up, so you can see that you get a point over here. Okay, then again for the next one, shift it up to 2. Okay, 2, this 1, 2, and 3. So 2 start minus 60, right, and so on, right? So after 3, then you shift another line of 20. Okay, just shift all this line, then join them together, and voila, you get your composite magnitude plot, right? So I hope that will be clear for you how you can construct this Bode magnitude plot, right? So next, come to the Bode 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 phase plot, right? Now the idea is similar to the magnitude. The only difference or difficulty is that, remember, in the phasor angle itself, okay, throughout our derivation we always talk about 10 decades before and 10 decades after, okay, where we construct our line. Okay, therefore in that case you have to get 10 decades before. Okay, one, okay, pull at 10 decades before is 0.1. Okay, and then 10 decades after, which is 10. Okay, we have to mark the start and the end of the pull, right? Then at the pull at -2, again 10 decades before is 0.2, 10 decades after, sorry, a decade after is 20, right? Then say similarly you just write down and then arrange them in the order. Okay, you have 0 0.1, 0 0.2, 0 0.3, 10, 20, 30. Okay, arrange them in the order. Same thing with your pool and zeros over here, arrange them in the order, right? Number. Okay, so that you can mark them up together, right? To mark all the particular point, right? So you can see that for the pool it's -45, right? -45, but then if you only that's why you have to write start and end. Okay, because this is where it start, okay, and then at this particular point it's end, it becomes 0. So just put a 0 there, right? So that it will be not being added up, okay, to this slope contributions to the phase plot, right? Phase, yeah, to the phase plot, right? Same thing for 2. So you start at 0.2 and go up to 20. Okay, becomes 0. Okay, so just plot them up and then total them out. Okay, so you will see that 45-degree, again same concept. Draw your 45-degree per decades line, draw your 90-degree per decades line. Okay, then shift all the line accordingly, right, to form your particular um, phase plot, okay, of the Bode diagram, right? So I hope that would be clear for you. If you have questions, feel free to post your comment, right, as we will address it when times come, right? So next, once we have that particular idea, then it's very similar for if we cannot factorize out in the form of a single order terms, then sometimes we have to deal with this kind of terms. Then we have no choice, then we have to deal with the damping ratio and omega n, right? Therefore we do the same thing again. We approximate the low frequency, high frequency, and at low frequency the angle and the magnitude would be, the angle will be 0 with the magnitude of omega n. Okay, so therefore the magnitude will be 20 log omega n square. Okay, at high frequency it is 180 degree. Okay, but then the magnitudes remain omega n. Okay, omega, yeah, okay, sorry, this one will be omega, right? So therefore again, once we put into our calculations, it will become 40 log omega. Okay, since this square in log, we just bring it out, multiply by 2, it become 40 log omega. When this become 40, meaning to say the slope will now be, instead of 20, it become 40 dB per decades. Okay, so it's twice time the slope of the first order terms, right? So again, we can normalize them. Okay, normalize by dividing by the omega n square. Okay, so we get this normalized and scaled form, right? And once we normalize them, we can start with 0 dB. Okay, we can start with 0 dB, and then with a slope of, instead of 20, we use 40 for a second order terms, right? 40 slope, right? Just draw, and this one represent our break frequency, right? Break frequency, or the omega n square, okay, which represent our break frequency over here. Okay, so for the phase plot, similar methods. Okay, but since it changed from 0 to 100 80 degree from 0 to 100 degree. Okay, again it will take 1 decade before and 1 decade after for this change to occur from 0 to 180 degree. Therefore, at the break frequency, or at frequency normalized frequency 1, okay, it will be at the 90 degree. Okay, so from 0, 90 and 180. Okay, so you will form this particular line. Okay, very straightforward. But then in actual, it is much more complicated. Okay, in actual it's much more complicated, where it depends on various parameter like omega n, omega, damping ratio, okay, which you can actually calculate the actual magnitude and the phase, right? So this is the actual line, right? So sometimes it's go downwards, okay, when the damping ratio is lower than 0.5. Okay, 0.5, then it start to curve down, okay, from your asymptotes, right? But then remember, our purpose is just to approximate. Okay, we let the actual one, let the computer to simulate. Right, so this is just an understanding for you that you, when you come across uh, second order terms itself, then therefore the curve itself will now depends on the damping ratio, right? Whether it go up or down, right? For Bode plot, which with denominator with second order terms, okay, it's just a reverse of what you have seen previously. Everything is just minus 40 degree per decade and minus 90 uh, at the break frequency for the phase plot, right? So this is again the how it would looks like, okay, for the 1 over second order terms, right? Come to the plotting. Okay, since I said you can easily plot using computer, yes, you can easily do that actually, right? uh, by using this command. Okay, you just go, if you use MATLAB, then you just go to MATLAB control system toolbox. Okay, then you just type this so-called command, right? Actually just type this in your MATLAB console. Once you already install the MATLAB control system toolbox, okay, then they will just plot this ZPK. Okay, ZPK is just a form of the numerator, okay, denumerators, okay, they will understand in the form of transfer functions, and then you use it to draw the Bode plot, right? So this is what you get, okay, in your console. Just type this, okay, you get your Bode plot, okay, magnitude plot and the phase plot, right? In Scilab, yes, okay, how about Scilab? Scilab, similar. In your console, just type your functions. Let's say is p equals to whatever you do previously, okay, but remember, these equations, remember you have s, right? Just follow back the previous. You have to define your s equals to a polynomial terms, right? So once you define that, you can type this on, okay, use a system linear form, okay, and then you put Bode p and you get the same graph. Okay, your Bode plot is ready, right? So what you need is just manually check, okay, where it's passed through, okay, and you will see how it's actually approximate for you. All right, so that's why I will not focus more on the second order. I will just focus more on how you actually construct that particular asymptotes. Okay, how you're going to approximate for the second order terms, I will just let the computer to do it, right? So if you want an examples on that, you can always scroll to the examples given at the end of the slide. Okay, if you scroll past through the last slide, the end slide of this uh, material, okay, given in the Google Classroom, you will see some examples over there as well, okay, taken from the textbook by Norman Nice. All right, Now come to this stability, gain, and phase margin using Bode plot. Okay, so now we'll start to grab on the ideas on how we would use it to for design. Okay, to select the k value, the gain value. All right. So we will start with this particular idea. As we have seen previously, we know that the root locus have this particular conditions where the magnitude must be equals to 1, the phase angle, right? The total summations of angle should be 180 degree. Okay, when we substitute this j omega, okay, into our system, then it should also in this form. Okay, meaning to say when this occurs, when this occurs, our system is marginally stable, right? When this occurs, okay, when this occurs, our system is marginally stable because it lies on the imaginary axis, right? So what we do is that if we want our system to be stable, the magnitude should less than that, okay, less than 1, okay, minus value would be good, right? So less than 1. So therefore in the case when we draw a Bode log magnitude plot, the magnitude should be less than 0 dB. Okay, this represent a 0 dB, a unity gain itself, okay, at the frequency which is equals to 180 degrees. So these two conditions must occur. Okay, remember why it occurs? Because when these situations or this condition occurs, our solutions of k will lies on the root locus. Okay, therefore we want it this magnitude to be obtained when the phase angle is 180 degree. All right, unity gain is 1. All right, unity gain is 1, this one. Okay, so remember we just use the k equals to 1. Okay, unity gain is 1, right? So at that particular moment, or when we normalize them, then the dB is 0 dB. All right, so we just take these examples to quickly illustrate how we can use that particular idea to actually obtain our gain. Okay, examples to determine the gain. So use a Bode plot to find the range of k which the unity feedback system is stable. Remember, unity feedback is where the feedback loop with the transfer function of 1. Okay, so here the transfer functions now is given as such. Okay, let's say if it is a open loop, it is very straightforward. All of this is at the left half plane and the open loop system is stable. But then when this is in a unity feedback system, we are not sure. Okay, so how to be sure? Either you use root locus technique, okay, to identify where is the locations of the root locus, okay, whether it will shift to the right half pole or not, or you can also use this frequency response technique. Okay, how you can do that is that we will start with checking where is 180 degree, okay, and what would be the gain at that particular point, right? So in order to for us to start, we will want to know the k value, okay, to be assigned here. Okay, so let takes it to be 40, okay, so that we get the so-called unity gain, right? So why we get 40? Because when we take the s approach j omega, then this becomes 0 0 and 0 at low frequency. Okay, so 0 0 0, so it becomes like 40. Okay, just recall back how we can get the starting value, right? So we get 40. So in order for we get so-called unity gain, okay, so we use k equals to 40, you get 1. Okay, and at that particular point our Bode plot will start with 0 dB. Okay, so once it start with 0 dB, then when we put it in, okay, you just put this particular value of 40, okay, you plot it in your Scilab or MATLAB, okay, you get so-called graph like this, okay, similar to this. Okay, so in exam I expect you not to use Scilab, okay, you just approximate using your asymptotes, okay, approximated line, okay, just as a practice. All right, so that you can obtain something similar to this. Okay, how we would interpret that later on is that we will start at 180 degree, right? So we're only interested with 180 degree. Okay, so we check 180 degree, okay, at this particular point, at this particular frequency, we map them up. Okay, and at this particular point we notice that it is equals to 20. Okay, it is equals to 20, right? So once this is equals to minus 20, okay, therefore now we can start to do some interpretations from that. Okay, so that Bode plot that we obtained just now, in order for it to be stable, as we have recall clearly, it must be less than 1 at the phase plot equals to 180 degree, right? So at the so-called 180 degree, the frequency is 7 and the corresponding magnitude is minus 20. It's fine, right? So in order for us to actually shift it, okay, meaning to say there is a gap where it be it has a gap such that it will remain stable before it become unstable. Okay, so if you adjust the gain by adding 20 dB, okay, if you start to adjust the gain by plus 20, then it will start to reach 0, and at that particular point the system will start to become unstable. Right, so this is the idea, right? So there is a 20 dB gain, plus 20 degrees gain, that the system will become unstable. Okay, so this 20 dB gain, okay, is represented by so-called 10, right? So we can see that since the gain plot is scaled for a gain of 40, right, and this 20 dB will just represent a gain of 10. Okay, therefore what we have now is 40 multiplied by 10. So 20 dB represent 10. Okay, we have to remember that. Okay, it's represent like 10 decades. Okay, so 10, right? So therefore previously we set k equals to 40. Okay, so meaning to say we have 10 multiplied by that particular 40, the gain itself. Okay, which means you have 400 for you to adjust. Alright, so for the stability itself, we will have a range of from 0 to 400 before it become unstable. Okay, when it reach more than that, you will notice that your curve will start to go to the positive side. Okay, your magnitude plot will start to go to the positive side, right? Then also we may want to define what we call a gain margin or phase margin, okay, which you can obtain it from the Bode plot again. Okay, so how we can obtain that? Okay, so this is your magnitude plot, okay, and this is your corresponding phase plot. Okay, so you may have your plot, okay, going up and down, okay, and particular point it will just cross, right? So again, our interest would be 180 degree and the 0. Okay, when more than 0 is unstable, right? So what we get previously is that 180-degree, we map it up, we see that there is this particular possibility for it to being shift up, okay, before it become unstable. We will call this as a gain margin, okay, the gain margin. Okay, for our previous case, our gain margin is 20, right? So this is our gain margin, whereas for the phase margin, it represents the change in open loop phase, where it shift, okay, in order for the phase angle, okay, to become again to become unstable, right? So you can see that it will occurs just a reverse directions, okay, taking at 0, okay. Then we plot and check what is this particular phase difference or phase margin, okay, where it allows the unity gain to make the so-called closed loop system to become unstable, right? So you have the gain margin and the phase margin being defined, but from the Bode plot, right? From the Bode plot, right? So just again take the examples on this, right? So referring to the previous example, if the k value equals to 200, find the gain and the phase margin. Okay, so you can say that previously the Bode plot is scaled to the gain of 40, and if we want to use k equals to 200, we need like 5 times greater, okay, 5 times greater. So 5 times greater, we have to use the log, alright, 5 times, okay, so 20 log 5, okay, which is equals to 13.98 dB, okay. So 13.98 dB higher, right? So on the same plot, okay, that we get previously, how we would adjust it or read it or interpret from that, okay, again 180-degree, okay, we get previously minus 20. What we do is that from that minus 20 we add 13.98, okay, which is minus 6.02 dB, okay. Therefore our gain margin would be 0.62 dB, okay, very straightforward, right? By taking the 5 times greater, okay. Then on the other side, okay, on the other side, if we want to get the phase margin, okay, then we have to draw it from the so-called magnitude plot 13.98 dB lower than the actual plot, okay. So this is our so-called actual plot, okay, 13.98 dB lower, okay, and then from that, which is occurs at 5.5, okay, and we just go through it, okay, you can see that is eventually we get 165, right? So why we try to get this frequency is that sometimes this is where it will occurs, okay, and estimated to be occurs, and also if we are plotting it on a graph paper, okay, which may not be like aligned correctly, so you just have to take this value, okay, and go to this 5.5 again, okay, you read, so you get approximately 1 minus 165. Therefore the phase margin would be the difference between these two, which is 15 degree, okay. So that is how you get the phase margin as well as the gain margin is, okay. Next we will go through these short parts, okay, before we call these sessions to an end, okay, because I don't want to have a super long sessions, okay, I guess some of you already sleeping, right? Okay, okay, now come to this relationship. This relationship is just an idea of how they are actually related to the closed loop transient as well as the closed loop frequency. Okay, this part just formula and just an exposure for you, okay, how you can use that, especially when you are getting the so-called peak time, okay, settling time, right, which you can obtain it from the experiment. Okay, that's why you can directly extract it and put it into your frequency analysis. Okay, so from that, okay, still here, good, right? So from that, you can use this idea. Okay, you can see that the derivation is that there is a relationship, okay, with respect to the damping ratio, okay, and the natural frequency. Okay, and also because of the damping ratio is related to the percent overshoot, okay, given as such. Okay, therefore we will also want to define it in the so-called frequency response terms. Okay, we call it as a bandwidth, okay, omega bw. Okay, so this bandwidth is actually being defined as minus or less than minus 3 dB. Okay, so in your magnitude plot, you plot a minus 3, okay, dB. So whatever after that, okay, we call this as omega bandwidth, okay, omega bw, right? So this is how you can get the omega bandwidth, and the maximum values at this particular point, okay, MP peak point, we call that as a resonance peak. Okay, so only a few so-called terms, okay, to represent the characteristics of the Bode magnitude plot itself. Okay, and this is where the equations come by. Okay, where you have the bandwidth frequency, which related to the damping ratio, okay, settling time, peak time. Okay, so that's why when you have like you are going to do a second experiment, all right, to form this so-called frequency analysis or Bode plot or whatever it is, then it will be very useful for you, okay, where you can directly integrate it from your experiment. Okay, you get it directly, okay, to get all this particular point omega bandwidth, then you can reverse back, okay, to plot your Bode plot. Okay, reverse back, okay, Bode plot, right? So you have all this Bode plot maximum point given by such, okay, omega n is such, right? So from that, this is how they are related to the Bode plot magnitudes. Okay, so I hope that would be clear for you. And this steady state error, I suggest I will bring it to the next sections. Only these last sections remain, okay, which I will bring it to the next sections, okay, so that we will use this uh, steady state error, okay, as we try to again design for the compensator. Somehow you may relate to the steady state error, right? So I think we bring it there so that it's kickstart easier for you, okay, and it's related from there onwards to design for your compensator using this so-called particular frequency response technique. Okay, you have learned the root locus technique. Okay, now we are using the frequency response technique to design for your compensator. Okay, the concept or the idea of the compensator remain the same. You have P, PI, PD, PID, okay, or maybe lag compensator, lead compensator, and so on, right? So that is the idea. All right, so I hope that's clear for you for today. Okay, we already almost 1 hour and more, 1.5 hours and more, right? So any questions so far before we end the sessions for today? Okay, so if no questions, then I guess we will end here, right? No, all right, great. Then we will end these sessions here, and just get ready for your tests on Monday. Okay, so if you have questions, then we will continue to answer, okay, your questions during the next sessions, as well as maybe tutorial, right? Okay, so that's all for me today, and have a great weekend, right? Okay, thank you and see you. Bye bye.